Data science has been becoming a growing profession and is also the heart of many organizations. That's why Data Science Portugal was born. The first community created by data scientists for data scientists. DSPT wants to gather anyone who works in the field and chat about any topic over this great subject. All members from our team are committed to make sure that the data science field evolves in a healthier and stronger way. To ensure that the focus is on sharing knowledge, we guarantee that our stage is not a place that supports any commercial or recruitment content, and our kind speakers are committed to share their experience for free. We want you. Let's do bigger things together. Join us at any event all around Portugal or online.
Hello everyone, I'm here with my father.
Hi everyone.
We are going to be the hosts for today. It's our 94th webinar. We're going to have a talk by Carlos Costa titled The Data Lakehouse for Simpler, Faster and More Integrated Data Analysis and Data Science. So this is the agenda for today. First, we'll have to hear us for 15 minutes while we explain all the schedule. Then we'll have the presentation by Carlos Costa. After, we'll have the question and answering. And finally, a networking for everyone that is up to it. Before going to the presentation, let's just briefly explain the group, our DSPT group. We are an informal community that gathers every kind of data science that exists, from the beginners to experience or senior field. And we want to break barriers between all the people involved so you can propagate knowledge more efficiently. Our main philosophy promotes knowledge sharing, open events for everyone, and breaking the barriers between what is a speaker and what is the audience. We just want to help everyone get foot on the field. What you don't want in our events, in our community, is selling, shameless promotion, or using the stage for hiring. Right? This is a place for sharing ideas, knowledge, methods. We want to help the community in that way. We are always looking for speakers. If you have any recommendation, if you know anybody that have done some interesting method work, it knows a lot about the field. If yourself is doing something related with the field, if you want to present your work for your peers, please use the link in the slides right now, fill the form, and we'll evaluate your idea for a future presentation. During the last years, we have been confined to the internet, right? But previously, in the good old times, we were divided in 5 cities: Aveiro, Braga, Coimbra, Lisbon, and Porto. Hopefully, we'll return with physical events in the 5 cities. And we have a website called datascienceportugal.com where you can find all of our events and a collection of events from the field from other organizations, right? You can also find job offers. You can post your events and job offers for other people to find. And it's a hub for finding data science related content. And finally, you can join us in any of these different social network accounts. A small note, the question and answer will be done using YouTube chat. So you simply write your question in the YouTube chat and we'll share it with the speaker. It will appear here as a banner and we can present the question in that way. So if you have any question during the presentation, just type it on YouTube. We'll do the rest. Without further ado, let's present Carlos Costa. It's our speaker for today. It's a director of data engineering foundation at Adidas. Properly presented with a hoodie in the picture. It's a nice touch. And he's an invited professor at University of Minho. He's going to talk about this, the data lakehouse for simpler, faster, and more integrated data analysis and data science. So welcome, Carlos. Thank you for the presentation, and we are going to leave it to you.
Thank you, Mario, and also thank you to the DSPT community. I'm very happy to be on another event in a community I always love to be part of. And welcome everyone. Thanks a lot for joining the session. You heard the title of the session. My mission for today is trying to, disseminate a bit more about the data lakehouse concept and how we can actually use it in our data related activities, either that is for data analysis, data science, or just data engineering in general. And this will be the agenda for today. So I will start with a brief motivation for why we actually need a data management system in the first place. So why do we actually need those kind of systems? Then I'll dive deep into what I consider to be the trio of data management systems. Then I'll also present some state-of-the-art, what I consider to be state-of-the-art Lakehouse open source technologies. So the technologies behind this movement, and then I'll dive deep into the features of Delta Lake and how we can use Delta Lake to make our data analysis and data science better by using the data lakehouse in a faster and in a simpler way as well. Just a short disclaimer before we start. So I just wanted to say that these are my opinions and interpretations of the state of the art. Okay, so everyone is different. Doesn't mean I'm wrong. Doesn't mean I'm right. I just wanted to use this content as food for thought. Okay, or ammo for discussion if you want. But if you have your own opinions, then I'll be happy to know more about your perspective also in the Q&A session. So starting with the motivation for having an adequate data management system. So before we actually start explaining what a data management system is and the types of data management systems we often find in data analytics, I wanted to show you a very typical pattern we found in several organizations. Hopefully not a lot of them, but sometimes it pops up here and there. And the first pattern we often see is what I call the give me access to the source pattern. So you basically have your transactional systems, whether that is your application databases or web APIs, whatever. That is where your transactional data lies. And you have data scientists and data analysts wanting to, do ML training, train machine learning models, execute ad hoc queries, or develop any BI dashboards, BI applications. And because they don't often have a data management system, what they ask is, I want to access the source directly. And this is, of course, a bad pattern to choose on your organization, because you most likely will not have a lot of stability in the connectivity to the transactional systems, because they are not analytical systems, they are transactional systems. So you either will face lack of connectivity, or the stability of the connectivity is not the best one you can get. And of course, this is also not a scalable approach, and it's not a performant approach, because as said, those systems are meant to process transactions. They are not meant to do any kind of analytical workloads. And because you are directly running analytical workloads on top of the transactional systems, there's a high chance you will blow up your critical system. So there's a high chance you can actually bring down an entire website for your company, or another CRM system, for example, if you are constantly pinging the source for more data and more analytical workloads. So this is a very wrong pattern to have in your organization. Hopefully we don't see it that much nowadays. And then we have kind of the opposite of the spectrum. And this is a very advanced pattern, by the way. It's what I call here the streaming pattern. So everything is a streaming. And in this context, you have your transactional systems, again, But in the middle, between analytics and the transactional systems, you have some sort of streaming platform. And this is very advanced. So if your organization has a streaming platform and runs a lot of streaming-based workloads or only runs streaming workloads, this is actually pretty advanced. But in my opinion, it has a couple of drawbacks. And the first drawback I want to point your attention to is this is very complex for data scientists and for data analysts to keep up with the stream itself. So dealing with streams is a very complex challenge, which is not often the case with batch workloads. So batch workloads are very different from streaming ones. So keeping up with the stream is highly complex. And because this is a streaming platform only, there's a high chance you will not have a huge history of data. So the streaming platform is not meant to store a lot of data throughout huge history, throughout huge periods of time. So you probably don't have all the data history that you need for your BI or data science applications as well. And if you are targeting online analytical processing, so your typical OLAP queries, there's a high chance your streaming platform will also not be able to keep up with the scale and with the performance that you need for OLAP as well. So the combination of these three factors actually make me think that okay, we might need to have, and we can have a streaming platform, of course. There's really a lot of value in those platforms, but it cannot be our only answer to the problem. And that's why very mature organizations or even startups that are starting now with proper data engineering in mind, the first thing that comes into your mind when you are designing an actual platform for analytics is having some sort of data management system. So it actually means the data flowing from your transactional systems run through some ETL/ELT, whatever floats your boat nowadays. The data flows through those processing systems, and they land into a data management system. And between the portfolio of data management systems, what I consider to be the three most popular ones nowadays is the data warehouse, the data lake, or the data lakehouse. And no matter the platform you choose, this is the community you are targeting to support every time. Your data analysts, sorry, the data scientists, and you are targeting to support machine learning, and you are targeting to support any sort of querying or any sort of organization. So that's the goal of the data management platform. And because I now introduced the motivation for actually having a data management system in your organization, we can dive deep into these three types of data systems. And the first one I wanted to talk about is the data warehouse. And if we take a closer look at the data warehouse, we have, of course, our sources, the sources of data for the company. It might be an external system, might be internal database asset, and you basically extract that data using some sort of either a commercial offering for extracting the data, so something like Fivetran, for example, or Stitch or Airbyte. Those are very typical data extraction tools, commercial offerings, software as a service often. But you might also want to choose Apache Spark, for example, or any other distribution of Spark, which I'm quite biased on Spark. I quite like the framework, so I also use it for data extraction myself. But if you prefer some type of graphical interface as well, a lot of people choose tools like Informatica or Talon also. And you have also offers from the cloud native services like Amazon AppFlow, for example. So those tools are meant for extracting the data from the source and making that data land on your data warehouse. So the mission for a data warehouse is to really store all the data that you need for analytical purposes. And I'm not saying this is like everyone follows this convention, But what we typically see in data warehouses is like they are divided in 3 layers. So you typically have landing/raw. So you basically extract your data as is and you don't process it. You just keep it there on landing. Then you have some sort of ETL/ELT tool to actually move your data and process it and shape it, massage the data a bit to make it transition from layer to layer. So you usually go from landing to the modeled layer or the curated layer, depending on your naming convention. And then you choose something like DBT again, which actually then you start baking some business logic. You start targeting a specific application or a specific dashboard. So you start shaping your data more and more according to your application or dashboard requirements, for example. And usually in a data warehouse environment, people tend to choose nowadays DBT, which is a SQL-based ETL tool that allows you to keep transforming your data between the layers of the data lakehouse. And in regards to the technological stack for actually implementing the data warehouse itself, we see nowadays people choosing Snowflake, BigQuery if you are on Google Cloud, or Amazon Redshift if you are on an AWS environment as well. So that's typically the technology options that people tend to follow. And in regards to data modeling, people are usually divided between flat tables or star schemas, so your typical dimensional model. And some people also go to the extreme of actually modeling the data in a Snowflake pattern as well, even if you are dealing with big data as well. But usually the community chooses one of the 3, whatever the team agrees, whatever are the conventions of the data community in the company. We often see flat tables or star schemas. That's mostly the typical pattern in data warehouses. And basically, then the mission of the data warehouse is to make that data arrive in the data analysis/BI platform. So that would be your Tableau, Power BI, Looker, Mode, whatever you want to choose there. And also make that data available for data science and machine learning. So make that data available for the platform that actually contains all the data science goodies, all the data science frameworks, and the machine learning engineering and the MLOps frameworks as well that data scientists and ML engineers actually need to make the machine learnings reach production grade levels. So that's basically it for the data warehouse. And in my modest opinion, there's nothing fundamentally wrong with following a data warehouse approach. But if you are a data engineer, you often question yourself, like, this is an environment where I mostly use SQL or I only use SQL. So it's basically, if you are coming from a DBT background, it's SQL based. So SQL is kind of the primary language you need to choose, or people often choose. And although the cloud data warehouses actually have streaming capabilities, the capabilities of those tools are often questionable. So if you are really targeting streaming applications, and if you really want to process streaming data in an intensive way and in a proper way, the data warehouse is probably not the right data management platform for you. Of course, if you are coming from a BI background, the data warehouse is usually fast as hell. So it's a really fast platform. Those are really performance-oriented tools for you to get the job done in terms of reporting and dashboarding. And it's also easy to manage. Like managing a data warehouse, I'm not saying it's easy, but I'm saying it's typically easier than the other data systems we'll see today. And it's pretty familiar to database administrators as well. So it's, at the end of the day, a relational database system, or very similar to a relational database management system, which a lot of people know already and a lot of people feel familiar with. But if you are coming from a data science background, you usually don't like the data warehouse that much. At least that's my impression, because it's mostly about structured data. you might go into the extent of actually having semi-structured data in there. It's perfectly possible, but it's mostly structured most of the times. And in those data warehousing offerings, you often don't have, or you really don't have, an open data format. In order for you to connect to the data warehouse, you actually need a data warehouse to be up and running. You don't have a way to directly connect to the data in an open way. And this creates, at least in my opinion, a lot of connectivity challenges, because you actually need the data warehouse to be there. You actually need some sort of data warehouse processing capability to get the data out into your data science platform, into your machine learning platforms as well. So the opposite to the data warehouse approach nowadays, kind of the data lake. And the data lake, I brought here another picture, and it's fairly similar to the data warehouse in terms of how I structured here. You still have your extraction tools as well, but and I also chose to divide it into 3 layers. You may have less, you may have more, but it's usually you make the data again arrive at the raw layer. But the tooling that you use to actually processing that data is often different. Like if you are working in a data lake environment, Spark is often the choice for you when it comes to ETL. You have other options like Flink or Apache Beam, for example, but Spark is by far the most popular project in the data engineering community. So you use Spark to move data between the raw stage into the lake or curated zone, where you already have some transformation, some filtering, some data quality constraints, and so on. And then again, finally, you also have the BI layer, the application layer, where you really have your data models oriented towards your data science models or towards your BI dashboards as well. And if we are talking about the stack of the data lake, is usually some sort of distributed file system in the cloud. So if you are coming from an AWS background, that would be AWS S3, might be GCS on Google, might be Azure Blob Storage if you are on Azure. And then because on the distributed file system, you only have files, it actually means you need some sort of metastore on top to actually create tables pointing to those files. And that's usually the Hive metastore for everyone. It's kind of the industry standard is the Hive metastore, although you have different flavors of it in different clouds, or you might choose to actually just run your own Hive metastore. And because the data lake has certain particularities, people often choose flat tables for the data lake. So if you are working with the data lake, some people actually promote star schemas, but the flat tables is by far the most frequent choice, because the data lake has some particularities that it's really difficult to tackle other kinds of data models. And also it's the one that usually provides you the best buck for your money. So it's like the best bang for your buck, I mean, because it's really the one that is able to ensure that you process the data as fast as you can. But then what it means is you probably, if you are targeting to support BI applications directly on your data lake, people often choose that the data lake is a bit slower than a data warehouse. So they start thinking about having a data warehouse on top, or some sort of OLAP store like Apache Druid, for example, where you actually replicate some data lake data and make it faster for BI. So it actually means you have two data management platforms instead of just one, to ensure the proper performance that the BI users need. And that kind of gives us some trouble that I'll dive deep later on. So it actually means if you are a data engineer, this is awesome for you, because you can choose between a lot of programming languages. If you are working with Spark, you can choose Python, you can choose Scala, Java, SQL, even R, for example. So you actually have a lot of choices. But the data lake, it doesn't support ACID transactions. And this is one of the biggest pain points the data engineers feel, because you don't have any kind of ACID compliance in the traditional data lake technologies. And this is actually a big pain point. It's much more of a pain point that it actually seems, and we'll dive deep into that later on. And you also typically don't have proper schema management nor proper data manipulation language. So if you are looking to have single row inserts, selective updates, selective deletes, you actually don't have any of that. So you either develop that yourself, or you start adopting the technologies that I'll talk about today in regards to the data lakehouse movement. So that's probably the biggest pain points that data engineers feel with a data lake. And if you are a BI user, then if you are connecting directly to the data lake, you probably feel that it doesn't match the performance that you are used to. It's really hard to get the performance right on a data lake, in my opinion. And I'm pretty sure most of us can relate to the small files problem on a distributed file system in the cloud. So if you have a data lake, if you are doing a lot of data processing, and then the output of your processing generate a lot of small files, it's really a nightmare to deal with those small files and the impact it has on performance as well. So it's really hard to get the performance right of a data lake. That's my first argument, which then leads to the replication into another data warehouse or into another analytical store like Druid, for example, which again leads to more complexity in the overall architecture and leads to more operational burden in your overall data architecture for the company. However, if you are a data science, you usually feel pretty happy about the data lake. You have structured data, you have semi-structured data, unstructured, so you have access to all sorts of data. And the data usually sits in an open data format. So it's usually Parquet for the structured data and semi-structured. You also have access to text files, images, videos, and so on. So really the data lake can store everything. And that's really cool for data science purposes, of course. And usually those data formats, they are deeply integrated into the ecosystem. So your data science, your machine learning tools are able to integrate with the data lake and get the data out without you having to need some sort of specific processing and specific connectivity requirements for you to extract data. This is because, for example, if you are using Spark to pre-process the data, you can directly access a Parquet file. You can directly access a text file. You don't need any intermediate technology in between your data science tooling and your data in the data lake, which was not the case for the data warehouse. And when it comes to the data lakehouse, fundamentally what changes is the introduction of new storage formats. So it's basically the difference between a data lake and a data lakehouse, in my opinion, is the ability to solve some of the data lake and the data warehouse problems by introducing new storage formats, and I'll dive deep into those later on. But that's the major change brought by the data lakehouse. We now have access to different storage formats other than Parquet, for example, which means we can get a lot of benefits both from the data warehouse and both from the data lake as well. So we have things like Delta Lake or Apache Ud, for example, which I will talk about later on as well. And in regards to the technology stack, is pretty much the same. But now it means that because we have these new storage formats, people can actually choose again to model star schemas, because these new storage formats, they enable ACID transactions for you. They enable proper schema management as well, which makes the modeling data in a star shape much easier than it was before in the data lake. So if you are a data engineer, you can again still choose Python, still choose any other programming language you want, including SQL, because you can still use Spark as a processing engine. You can still use Flink or any other tooling of your choice for doing the ETL, So you still have access to a lot of programming languages. You now have ACID transactions because these new storage formats like Delta Lake, they enable those ACID transactions for you out of the box. And they also enable proper schema management and also proper data manipulation language. So you can actually do single row inserts, selective deletes, and selective updates as well, which makes it far easier to work with things like star schema. So if you are familiar with slowly changing dimensions and those kind of topics, they become much easier with these new storage formats. If you are coming from a BI background, then these new data formats, they allows us to have several optimizations that make the BI workloads faster. So you have access to a lot of optimizations that the storage formats have out of the box, which makes you able to have better performance for your BI workloads as well. So these storage formats actually target BI as well. That's where we start seeing the data warehouse capabilities merging with the data lake capabilities as well. And also, the goal of these storage formats is also to make it easier for everyone to work with the metadata and also to have some governance capabilities on top of the data lakehouse. And I will show you some examples later on how some governance capabilities work as well, and now it makes everyone's life easier. And if you are a data science, it's more of the same. So you continue to have access to all types of data because you can have Delta Lake formats, for example. You can continue to have Parquet. You can continue to have text files, images, videos, and you can mix a lot of stuff in the data lakehouse because at the end of the day, it's still a data lake with a new storage format whenever needed. And it's deeply integrated into the ecosystem because Delta Lake, for example, or Apache Ud, those are open formats that Spark can connect to. You can connect from other tooling as well that is used in the data science and machine learning environments. So you actually don't need special processing engines to deal with these new data formats as well, which is a big thing. So to wrap it all up, we can say that we have 3 data management systems, and they both, in my opinion, have good things, bad things, and some of them ugly things. And just recapping, the data warehouse is very good for BI. It's very easy to manage and to access the data warehouse, but in my opinion, is bad for unstructured data. So you don't have the capability of handling unstructured data in the data warehouse. The streaming capabilities of a data warehouse are questionable, and it's a SQL only or SQL mostly environment. Like there are some data warehouses which have some side languages besides SQL, but it's not at the same level as something like Spark, for example. And the ugly, in my opinion, is that this is kind of an alien to the data science ecosystem because you don't run data science inside the data warehouse. So the data warehouse is always a source of data for you. So it's kind of a database that is there for you to get data out and do something else in another platform, which is not the case for a data lakehouse or data lake architecture, where some of the tooling you use for engineering the data lake is also some of the tooling you use for data science, something like Spark, for example. And when it comes to the data lake, the good things is you can handle all volumes of data, all varieties and velocities of data as well. You have the ability to choose between several programming languages. You have awesome data science integration because the tooling just integrates almost natively. You have, although some bad things as well, of course. So you have lack of ACID capabilities. You have lack of proper DML, data manipulation language, and also the lack of proper schema management as well. And in my opinion, the ugly stuff for the data lake is really that most of the times you really need to replicate data into a BI or OLAP-oriented store, a data warehouse or something else to make your BI run smoothly, run concurrently, and fast as well. So this brings another layer of complexity because you have to really replicate a lot of data and make sure that that data is replicated properly for BI workloads. And basically, the good thing about the data lakehouse is that it tries to combine the benefits of both. So all the good that you have from the data warehouse and the data lake, you should always you should also have it in the data lakehouse. If we are talking about the bad stuff, it's not so bad, but it's something to consider for sure. It's like the performance of the data lakehouse is heavily influenced by the querying processing technology. So if you choose Spark to process the data in the data lakehouse, you might get some performance numbers. If you choose something like Presto, for example, you get other numbers. So you also choosing the querying engine is a big part of actually choosing the data lakehouse architecture in the company as well. And in regards to the ugly stuff, who can tell at this moment? I'm pretty sure it's still there to pop up, but not something we can point at this moment. And starting to really talk about the technologies behind the Lakehouse movement, and I'll just bring today open source technologies. I'm a huge open source advocate, and it's usually when I give some technology guidelines, I try to go open source whenever possible. And basically, we have three main technologies behind the data lakehouse movement. And the first one I wanted to introduce you is Apache Ud. So Ud was open sourced by Uber. So it was an internal development done by Uber, and they open sourced it. And basically, Ud stands for Hadoop Absurds, Deletes, and Incremental. So this was basically Ud's approach to extend the Hadoop capabilities to actually deal with absurds, with deletes, and with incremental updates to the data lake. And basically, the mission of Ud is to bring transactions, record level updates or deletes, and change streams to data lakes. So change data capture also to the data lakes as well. One curiosity is that Apache Ud can use Parquet underneath. So basically, Parquet is still one of the storage formats behind Apache Ud. And if you are interested about the project, you can just check the documentation. They have a really extensive documentation on the project. And another project of that I also have a lot of interest in, it's Iceberg. And Iceberg is also an Apache project. It was open sourced by Netflix. And basically, the mantra of the project is the open table format for analytical data sets. And the community of Iceberg, they describe the project as Iceberg is a high-performance format for huge analytical tables. Iceberg brings the reliability and simplicity of SQL tables to big data. So I'm actually reading the missions of the tools, because I will for sure not dive deep today into a comparison between them. They are, some of them at the early stages of development, different levels of maturity between them. And if I say something today, it will be a lie tomorrow. So I will definitely not go into concrete comparisons between them. They do more or less the same. They have more or less the same capabilities. So if you are interested particularly in one of them or in all of them, I'm just linking you the projects and giving you the mission, the overall mission of the project. But again, the mission is the same for all of them. Implement the data lakehouse capabilities in a company or in an open source project. And basically, Apache Iceberg can use Parquet underneath as well. So it's also a storage format that you can choose. You can choose others if you want. And it's providing transactional capabilities on top of Parquet, much like Ud as well is doing that. And final one, and I must confess, I'm biased. This is my favorite one, but you are free to do your research. And basically, the last one I want to present you is Delta Lake. And this is the one I'll also show you capabilities in a second. And basically, Delta Lake was open sourced by Databricks. So if you don't know Databricks is the main company behind the Apache Spark project as well. the main contributors there. And basically, Delta Lake's mission is to build lake houses with Delta Lake. And from the beginning, Delta Lake was immediately associated with the Lakehouse architecture. If you see the other missions of the other projects, for example, you actually don't have the word Lakehouse in them. And Delta Lake, from the beginning, was targeting to be coined with the term Lakehouse as well. And they are really huge advocates of the data lakehouse architecture, which is also getting them some attention to the project as well. And basically, they describe the project as an open source storage framework that enables building a lakehouse architecture. So again, a lakehouse architecture with several compute engines. So you can actually choose several compute engines to process the lakehouse data. So it might be Spark, might be other projects that support the Delta Lake format. And another curiosity, the Delta Lake only uses Parquet underneath. So the other storage formats, they can use Parquet or something else. And the Delta Lake only uses Parquet. So basically, the mission of Delta Lake is to provide transactional capabilities and other capabilities as well on top of Parquet. So basically, the last item for the agenda today is to really show you some of the features that you can use in Delta Lake to implement a data lakehouse and to better support data analysis and data science. So I hope you find some of these features useful. I'll try to make it as practical as possible. Although it's just slides, my mission here is to make sure that you can get some ideas into your day-to-day projects or into your personal projects as well. And the first feature, of course, I want to show you is ACID transactions. I've been speaking about ACID transactions the entire webinar, so it's actually I needed to start with ACID transactions. And what it basically means is that by using Delta Lake, readers see a consistent snapshot view of the data since the start of the query. So even if the table was modified since the start of the query, you always see a consistent snapshot view of the data from the beginning of your query. So you have read consistency here. What it actually means is that multiple writers, so if you have several applications, several pipelines, writing to the same table partition or to the same table, they can write data concurrently. And if you are coming from a data engineering background, you know what sorts of problems this can create on a data lake. Now with Delta Lake, you actually can have concurrent modifications to a table and to a table partition, because those writers that are writing data concurrently, they will always see a consistent snapshot view of the data, because when you start writing, you actually read something, so you basically have the same capabilities of a reader that sees the consistent snapshot view of the data. So you always have that for multiple writers, and we always ensure a serial order for these writes. So you have isolation between those write operations as well, between the concurrent writers. So this is really important to ensure ACID transactions. So the general steps, they look more or less like this. So you read the latest state of the table to identify the files that need to be modified. So that's the first step. Then you stage the files you need to write. So the new files you are about to write with the new data, they are staged. There is a validation to see if there are conflicts or not to the transactions that were done since then. And if there are no conflicts, then Delta Lake commits the write operation, which means now new readers are able to see the new data. And if you are coming from a Parquet-only background, you know how painful that can be in data lakes, because you don't have any of this insurance in Parquet. And basically, this is our Delta Lake table looks like. So you have the folder of the table. You have of course your partition. So if you are familiar with table partitioning, you have one folder for each partition value, but you have an extra folder for Delta Lake. So although here you have Parquet files containing the actual data, you have an extra folder which is called the Delta Log folder, where you have several JSON files, and those files are basically a transaction log of everything that has happened to the table. So inside those JSON files, you find things like the file 2.parquet was added and the file 1.parquet was removed. So all the operations that happen on the table are tracked here in those JSON files. And for each 10, and in between each 10 JSON files, what Delta Lake does is actually stores a checkpoint Parquet file to make us able to read the Delta Lake log faster. So if you are doing a lot of transactions on top of your table, if this was all JSON data, then you know that JSON is not a very friendly analytical format. So what basically Delta Lake does is it does some checkpointing for each 10 files, and then we just process the Parquet files to see the transactions that happen to the table and figure out if there are conflicts, if there aren't any conflicts, and if we can commit, and what Parquet files to actually read from the table. So basically, when you query the table, you first inspect the Delta Log, you see the latest state, you see the Parquet files that you need to read, and then you actually read the Parquet files which contain the data inside the partitions. What we also have with Delta Lake, as promised, is a comprehensive data manipulation language, or DML. It actually means that you can do selective deletions on the data, which they were not there before. So if you are using a Parquet-backed table, you cannot delete specific rows. There is no such capability on Parquet. You now have it with Delta Lake. So if you want to delete specific data from your table, you can actually run selective deletes. You can also update a specific portion of your data. And this is a very awesome capability that you have on Delta Lake. You can actually do upserts on the data by using merge statements. So you can merge the existing table, the data on the existing table, with new data based on the merging conditions. So you can decide, you can figure out if a specific row with a specific pseudo primary key was already there or not. And if the data was there in the table, you can choose to update it, as we are doing here. And if the data was not there in the table, you can choose to insert it. Or for example, if the data was there, but it matched a specific condition, you can choose to delete it. And you may ask, why is this relevant? And for everyone doing incremental data processing on the data lake knows how much of a game changer this actually is. Because dealing with incremental updates or dealing with change data capture in data lake is really painful for data engineers. So it's actually a very cool feature. One of the biggest selling points for Delta Lake for sure. Another topic that I wanted to show you is how Delta Lake tackles schema. So you have two options. You can either choose to enforce the schema of your table, or you can choose to automatically evolve the schema as well. And schema enforcement is actually a very cool feature, because if you have a pipeline that is writing new data to a table, and if the source, for example, has introduced a new field or has changed the data type of a field, you might choose to fail your pipeline immediately. When you try to write to Delta Lake, it will say that the schema doesn't match, and then it fails the entire transaction. And you didn't have this with Delta Lake, with Parquet data lakes, sorry. So you actually needed to check for yourself the schemas and if there are any mismatches or not. And Delta Lake does this automatically for you. And if you don't want to enforce the schema, you can actually choose to evolve it. So when you write the data, we are using Spark here. So if I do a write with the option merge schema, I can actually choose to evolve the schema automatically. So if a new field was added, or if a data type of a field was changed, I can tell Spark to automatically evolve the schema of the Delta Lake table, and those schema changes will be automatically reflected in my table. So that's also a very cool feature, but please use it with caution, because of course you may have several downstream systems which are consuming your tables, and if you change the schema on the fly without noticing everyone, then you might face into some downstream issues later on. If you want to set it across the Spark session for all your cluster jobs, or for every job that is doing multiple write operations on Spark, you also have an option to set it globally, the schema evolution feature. And if you are completely overwriting the data, you can choose to completely overwrite the schema as well. So if you don't want to evolve the schema by merging the old schema with the new one, you can choose to completely overwrite the schema and overwrite the data as well. Another cool feature that Delta Lake has is constraints. So you can actually choose to put a constraint on a specific field that tells you that that field should not be null, for example. Or you have other constraints, which are the check constraints, which allows you to put Boolean checks on top of your Delta Lake table. So you can say that for each insert on the table, for example, the date field should be higher than a specific value. And you can choose the Boolean expression you want. And this is, in my opinion, one of the coolest features to have in regards to data quality, because it's a very simple solution to a very complex problem. Like, tackling data quality is really complex. And of course, this doesn't solve all the data quality problems in the world, but it's a first gate for data quality, or one of the first gates to data quality, that allows you to have some sort of quality assurance on your Delta Lake tables without you having to write any code. You just put this constraint on the table, and for every insert, Delta Lake will actually validate those constraints against the data you are trying to insert. So you don't need to overcomplicate the problem with something like PyDQ or great expectations, because you have some basic capability here. Of course, it's not the same capability again, but it's some level of data quality, I would say. And this is a mix between a Spark feature and a Delta Lake feature. So it's not really Delta Lake specific, but it's something that I wanted to show you today, because especially with Delta Lake, you can write the same code both for batch workloads and for streaming workloads. And sometimes we think about streaming as this hugely insane complex problem, that I need to write specific streaming code to deal with streaming data. But if you are using Spark, and if you are using Delta Lake, it's actually simpler than it sounds at first. So let's take this example here. We are reading a Delta table. So this is the way I do it in Spark. So spark.readStream, the format is Delta, and I point to the location of the Delta table. I can also point to the name of the Delta table, but for now we'll use locations on the file system. So here, what I'm basically doing is to read streaming data to a data frame called events. Okay, and then I'll transform my data. This is not a talk about Spark and how to transform data in Spark. So if you are familiar with it, then you are just transforming the data using the Spark API. Then I can also write the data as well in another table. So here I'm choosing the write stream options to write the data. The format is Delta again, so I'm basically reading a Delta table, transform it, and write another Delta table with the results of the transformations. And this is a very cool option to have in Spark. It's called a checkpoint location, and it basically allows you to store the checkpoints of your stream. So all the data that was already processed by your stream is indicated here in the checkpoints. So when you resume the stream, the stream will be picking up data since the latest checkpoint, since the last checkpoint. And if you keep a constantly running streaming job on Spark, of course, your streaming will just keep running. You have a live cluster running your stream. And if that's your use case, that's fine. You can just keep running the stream and keep processing the stream. But if you want to know how to use streaming code for batch workloads as well, and never have to write the same code twice for batch and for streaming, there's a cool feature you can use in Spark, which is the trigger option. And with the trigger option, you can choose to trigger the workloads in a trigger once mode. And it basically means you can run this job every day, once a day, for example, or multiple times a day. You can choose a certain schedule to run the job, to bring the cluster up and run the job. And you will always pick up the data since the latest checkpoint. So you don't need a live streaming connection. You can actually bring a batch job up, run the pipeline. The checkpoints folder will contain the latest state of the data that was read, and you just read the changes since the last checkpoint. And you don't need to figure out like incremental, how to tackle incremental loads, read from a certain timestamp, and so on. By using the checkpoint location and by using the trigger option, you can run a batch workload as you would run a streaming workload as well. So that's pretty cool. And I wanted to brought this tip of the day for you in this session. Another cool feature that we have on Delta Lake is what we call the Audit History. And it's basically an option that you have on Delta Lake, which describes the entire history of operations that were executed against the table. So you can run the describe history command for the table, and it will show you the full history of the table or the latest version only if you want. And you can also write the same code in Spark. So you can write it in SQL or you can write it in Spark. It's absolutely fine. The API is pretty simple, as you see here. And basically, this is the output of the command. So for a specific Delta Lake table, you have access to all the versions of the data of the table. So for example, we can see that version 1 was a delete after version 0. I don't have version 0 here in the screenshot, but version 1 was a delete operation after version 0. Then an update was executed, then a delete and an update and a delete again. So I can actually see all the operations that have modified my table. And here we can see, for example, the number, the total number of rows that were modified, inserted, deleted. I can actually, if I have access in my specific environment, I can check, for example, the job or the cluster ID that modified the data, also the user or the timestamp associated with a specific version, with a specific commit to the Delta table. So what it basically means is that this gives you a Git log kind of functionality for your data. So this is actually Git functionality, versioning control for your data and not only for your code. And this is actually one of the biggest game changers in Delta Lake as well. It's kind of this history, this version control capability that Delta Lake has. And of course, if you have access to the history, you also have access to time traveling. So you can actually travel back to a specific version of the table just by providing two options. You can choose to go back to a specific timestamp, or you can choose to go back to a specific version of the table. So if you see here again, we had specific versions and specific timestamps associated with those versions. And you can always travel back to those versions by using the version or the timestamp you want to travel back. And this is very simple to do it in Spark. So it's again spark.read.format delta, but you provide the extra option of the timestamp or the version to not read the latest version of the data, but to read a specific version that you want. And we can use it for several use cases. You can use it, for example, for reinserting deleted data. So let's assume you accidentally deleted user data, for example. You can just read the Delta Lake table again, provide a timestamp of yesterday, and choose to load that version of yesterday, for example. And what you can actually do afterwards is you can choose a specific user, the user to which data got deleted, and you can choose to append that data back on the table again. So you can actually recover from a specific, from a previous version as well. So again, making the relationship with Git, this is kind of Git reset for your data as well. So you can always reset your data to a previous version that you had before. But you can also use it for analytical purposes. You don't need to use it for fixing problems. You can also use it for analytics as well, which is pretty cool. Because you can actually, again, read the Delta table as it was last week, for example. I can run, for example, a count of the distinct users that I have on the table, and I'll store it as the last week count, for example. And then I can choose to read the table as it is now, the latest version of the table. I run the same count of distinct users again. And then what I can do is do the difference between the count as of today with the count as of last week. So I can compare, for example, my customer growth since last week. And this is also some cool analytical capabilities that we can leverage with Delta Lake. So a tip for the data science community is you can use, with time traveling capabilities, you can easily use Delta Lake tables as a feature store because you can store your customer data, product data, you can store images, metadata, for example, you can choose to store store data or warehouse data. All the features you may need for machine learning models, you can choose to implement a Delta Lake table or a set of Delta Lake tables for your feature store, because you have ACID, you can modify every row, you can time travel between different versions of the table, which allows you to have reproducible experiments. So if you are a data science or a data scientist or a machine learning engineer, you want to have reproducible experiments. And having reproducible experiments means, version your code, but it actually means version your data as well. You need to run your experiment in the data as it was last week. So if your data was modified since last week, you still need access to the data as it was before. And if you are doing this in a data lake, it's very difficult to ensure that. But now with data lakehouses and Delta Lake, you can choose to run an experiment by traveling back to the data as it was last week. So actually having Delta Lake tables as a feature store is a very good idea. And you can do all sorts of analytical things as well with Delta Lake. You can, for example, read the changes between two different versions with the except clause, for example, and you can figure out, like, from now onwards, I just want to process the data that is new when compared to last week. So all my pipeline, my entire pipeline just processes the difference in the data between this week and last week as well. So you can also leverage Delta Lake for that. And we have several optimizations as well in Delta Lake. I mentioned that this storage format and the data lakehouse is meant to also support BI. And the big part of supporting BI is actually to optimize the layout of the data. So I talked about the small files problem on a storage system like S3 and how it impacts performance. With Delta Lake, we have a special optimize command that optimizes the sizes of the files in your Delta Lake table, either the entire table or a subset of the data. So you don't need to care about small files anymore. You just run the optimize command, and it will compact the data in an optimal size format for you, in an optimal file size for you. And another feature that Delta Lake has is data skipping. So basically, Delta Lake collects a lot of statistics in the Delta Lake files, and basically through those statistics, the minimum values and the maximum values for each file, Delta Lake is able to completely skip files if they are not needed for answering a specific query. And this is actually a very good feature. You don't need to do anything else. It's just enabled out of the box. You can configure the amount of columns for which you collect statistics. But other than that, you don't need to do anything else. And it will just skip unnecessary data for you. So a performance tip for everyone, it's use it in combination with ordering or sorting your data before writing. So if you sort your data in a specific way before writing it, in combination with these statistics here, it makes a lot of difference for the columns that you use a lot for filtering, for example. On top of partitioning, data skipping is actually a very good practice to have in Delta Lake as well. And finally, I promise is the last slide. I hope it's being useful to you, but I also know it's a lot of content, and I promise this is the last one. I just wanted to finish the presentation by talking about Delta sharing, which is kind of a new project. It's very recent. It's even more recent than Delta Lake itself. But basically, the Delta Lake community, they are creating a protocol called the Delta sharing, which will allow you to share Delta Lake files directly to the consumers. So you don't need, you actually don't need a lot of intermediate processing between the consumption and the Delta Lake files in the Data Lakehouse, because you will be able to access the Delta Lake files directly from a consumption tool like Power BI, Tableau, or Presto, for example. The people with the right permissions, the permissions are granted through the Delta sharing server, would just be able to, by using a credentials file, just use that file to load any Delta Lake files directly into the consumption tools. So this is very useful for you to share data with external organizations, for example, because they don't need to have Spark. They can just access the data directly through Tableau, for example, or even between the teams within your organization. This might also be a good solution to quickly share data without, exporting Excels and CSVs and so on. So it's actually a very exciting protocol. It's still on the early developments as well. And of course, you can choose to connect directly to it, but you also have ways of reading it directly in Spark if you want to still use it for some sort of data processing. You can read it directly on Python. So if you are not running Spark, for example, you can just use pandas to actually load the Delta table and read the data you need. So it's a very exciting project. If you are keen to learn more about it, just feel free to consult the link. And yeah, keep looking at it, because it will for sure provide a lot of benefit in regards to sharing data between teams and between companies as well. And that's it from my side. Thanks a lot for attending the session. I hope it was useful to you. And just feel free to ask me anything. I'll try my best to answer the questions.
Okay, we have a couple of questions here, but I will let Mafalda do the first one.
The first question is, Joanna, how is the data versioning manager? How can we compare with other platforms for data versioning, such as DBC?
Okay. So I'm not sure to which level of detail I should go in regards to data, how is data versioning managed. But if you check the Delta log files that I talked earlier when I talked about ACID transactions, it's the way we can figure out the changes to the table and the different versions of the table. So if we inspect the delta log files, we can actually see the different versions and the files that were added or removed in between versions. So basically, the delta log functionality, in combination with the ability to processing the delta lake format, is the way we handle data versioning and the ability to travel back to different versions. So it's a combination of the delta log, all those JSON files, with a processing engine like Spark, which is able to understand the Delta Lake format as well. So it's basically a combination of Spark capabilities and Delta Lake capabilities. And when I say Spark, I mean Spark or any other tool that can understand Delta Lake. So basically, the Delta log is the engine behind the data versioning mechanism, and how it compares to other platforms for data versioning. I personally don't know DVC. I know there are some Git-like data platforms which are targeting data version control, but I cannot, unfortunately, dive deep into how it compares to other platforms. I can compare it to the other storage formats like Ud, for example, which also provides time traveling and so on. But they are basically the same. As said, they provide the same level of functionality, some with different levels of maturity than others. But in regards to a specific platform, sorry, I cannot dive deep into that. But I'm pretty happy to stay afterwards and understand your question a bit better.
So this is a question for the networking part. Next, we have one by Multi-City Tech. Do you think that the data lake approach requires more or less man work, more people, more teams, compared to other approaches?
Yeah, I would say definitely requires less, I would call it people work, to be completely inclusive. It's definitely requiring less than the data lake. Because as said, the storage format itself, like Delta Lake, is meant to provide you out-of-the-box functionality that you didn't have in data lakes. So things like managing ACID, managing incremental updates, managing selective deletes or selective updates, they were not there in data lakes, which actually means that if you are a data engineering team, you need to build that yourself in your framework. You need to figure out how to do the incremental changes. You need to figure out how to restore a previous version of a table if it got corrupted, and so on. And Delta Lake, or in fact Apache Ud or Iceberg, they really take away all of that effort from your side. And on the BI side, it also enables you with better governance and faster access. So you don't need to. Our approach is always, before you actually think about replicating all the data you have on the data lake for BI purposes in another data warehouse or in another database, evaluate if the data lakehouse is not able to provide you that benefit already with the performance that you expect. And if that's true, then just use the data lakehouse and you will save a lot of hours from your engineering team by having to deal with a data warehouse plus a data lake plus a couple of databases flying around. If you really implement the data lakehouse approach, I really believe that it requires less people work than actually other approaches. I wouldn't say the data warehouse. I mean, it's probably a bit more complex than the data warehouse itself. But the data warehouse doesn't provide you the same level of functionality as the data lakehouse does, in my modest opinion, and according to some literature, of course.
Okay, thank you for the reply.
Okay, next question is, which is the query language used for DML action on Delta Lake? Syntax looks similar to HQL.
Yeah, so it's basically Spark SQL. So it's basically it's basically a SQL language. So DML actions are very familiar to what you would write in any other SQL database. It's Spark SQL, and yeah, I wouldn't say it's ANSI SQL on those operations. I'm not really sure if the merge operation looks the same as in, let's say, SQL to 2003 or ANSI SQL. I don't know, but it's definitely something very similar to standard SQL.
Thank you.
We have again Joanna with what kind of data quality rules can we define?
Okay, so maybe I can go back to the constraints because it's really not that extensive. So it's not meant to be a data quality framework by any means. So if you are coming from a great expectations background or from PyDQ, those systems are much more capable of the data quality checks you can write. But basically what it means is that you can add a constraint, like as many constraints as you want, with any Boolean expression you can think of. So you can basically write any Boolean expression, combining your fields, combining different Boolean operators, and you can write as many constraints as you want. Of course, the more constraints you put on the table, the more intensive it becomes to do all those checks in each write. But yeah, you can just basically choose to write any data quality rule that can be expressed as a Boolean expression. That would be my answer. So, for example, things you can't do. You can't really aggregate a column and see if the count of that column or if the sum of that column is higher than something. That is not supported, for example. So it needs to be row by row checks. So row level checks, I would say.
Okay, thank you for the reply.
And the last question is, if we are saving the checkpoints and Delta Lake give us power to retrieve or restore the deleted data from any point in past, does it stores every version as if? If yes, won't be too much volume of that data?
Yeah, that is a really good question. And basically, the way Delta Lake figures out the changes in between the versions, it's not by really storing all the data again for each version. What it does is really through the Delta log files and through the Parquet files that are kept there for a certain period of time, it figures out in a specific version. So let's call it version 5 and version 4. It knows through the Delta log files that version 4 uses this set of Parquet files. And version 5, let's say 10 Parquet files were deleted and 20 new Parquet files were added. So it basically knows that if I read version 4, I need to read these Parquet files that are still there. And if I read version 5, I need to ignore the 10 Parquet files that were deleted and read the new 20 Parquet files that were added. And you may ask now, okay, for how long should I store the Parquet files that got deleted there? Because if I need to travel back to a specific version, I need the Parquet files that were deleted still there. Otherwise, I wouldn't be able to read the data. And what I didn't show you today is Delta Lake has a special command which is called the vacuum, and it basically cleans up older versions of the table. So, for example, versions older than 7 days, if you run the vacuum command with 7 days threshold, it cleans the data that is older than 7 days, which means all the Parquet files that were deleted 7 days ago or earlier will also get completely deleted. And after that, you cannot really access the older versions of the table that were 7 days or earlier. So it basically, you don't store data forever. You have this vacuum command The way you figure out the data to be retrieved for each version is through the Delta log files. And you also don't store the entire table again in between versions. So between version 4 and between version 5, we are not talking about the same data replicated in each version. We are talking about a set of Delta log files that know which files got deleted, modified, or added. And in that way, when you read the table, you figure out the files that you need to read. And that's basically it. I hope the explanation was good enough. I tried my best, but please let me know if that was not.
Okay, that was the last question. Thank you so much for the presentation. For everyone still in the stream, you can continue your discussion in the networking part. We just have a couple of slides to show, and you can all go to the networking part.
Okay. I want to say, first of all, thank you, Carlos, for the amazing presentation and for accepting our invitation too. And thank you guys for being here. And don't forget our call for proposals. We really want to share your work or share anything that you are passionate about. And without further, let's go to the network session where you have the link in the YouTube chat, I think. And see you guys there. Thank you, everyone.
Data science has been becoming a growing profession and is also the heart of many organizations. That's why Data Science Portugal was born. The first community created by data scientists for data scientists. DSPT wants to gather anyone who works in the field and chat about any topic over this great subject. All members from our team are committed to make sure that the data science field evolves in a healthier and stronger way. To ensure that the focus is on sharing knowledge, we guarantee that our stage is not a place that supports any commercial or recruitment content, and our kind speakers are committed to share their experience for free. We want you. Let's do bigger things together. Join us at any event all around Portugal or online.